So, we had simply formulated the resolution rules. We had 4 rules in the resolution for first order logic. One was your binary resolution, which is just like your resolution in propositional logic, okay. But along with most general unifier now. Then the other rule was the factor rule, okay, which unifies a sub clause of the clause, then takes or applies that most general unifier on the whole clause, that will be considered as deduced from the original clause. Then you have the paramodulant, so which is specially for the equality predicates, okay. There if you have 2 clauses, one is having some equality literal like say t equal to u, and then the other one is having some formula where s occurs, s is another term. Then you take most general unifier of s and t, call it sigma. Now delete t equal to u, delete x of s, add x of u, and then to the union of those 2 clauses, and then apply your most general unifier sigma, that was the paramodulant. Then we have another equality axiom, which we wrote as a rule, that is anywhere you can introduce t equal to t. These are the 4 rules of resolution. Then we wanted to discuss one example. So, the earlier example which says everyone who buys a ticket receives a prize, therefore, if there are no prizes nobody buys a ticket, right. That was the example we are considering. So, let us write it in first order logic. So, we start with everyone who buys a ticket. So, there is a ticket which x buys, then that person x receives a prize. So, there is a prize which x receives, okay. That was our only premise. Therefore, if there are no prizes, then nobody buys a ticket. Okay. So, this is the consequence we wanted to prove by resolution. So, first thing is we have to use deduction theorem or RAA whatever, then bring it to the clausal form, fine. So, we will use both deduction theorem and RAA. So, first this one will be taken to the premise side, next this one will be taken with negation sign. So, double negation we are using, so we will just omit it. That is, we have for each x there is y, ty and bxy, implies there is y, py and rxy. Along with that we have not, there is x px, and then we use RAA. So, we have the other one, there is x, there is y, ty and bxy. This should entail bottom due to deduction theorem and reductio ad absurdum. Okay. Next we take them into closure form without sharing a variable. Clauses should not share variables, right, that we have to take care. Okay. So, first is from this one, first one says for each x, this becomes for each y when goes out. So, that is the other one comes as there is. So, we rename this, there is z, this y becomes z now, ty and bxy implies pz and rxz. Okay. Let us write the same way. Next, the other one is almost in the form. So, that gives for each x not px, we are going to omit the universal quantifiers. So, better to keep it in that form. Next, but x is already used, let us write it as u. Okay. Next, we have two existential quantifiers, okay. There is no for all before it. So, they will be simply replaced by some constants, Coulomb constants, which will be new to the all the consequences, everything this would be new. So, you write T A and B, let us write B here, A B, it is not necessary, but let us write that. So, this is the set of clauses, but it is not a clause first one. So, let us bring it to that form. So, there we have for each x, for each y there is z. So, you have to use Coulombization. So, its Coulombization z might depend on x and y, but z occurs only with x in a predicate, with y it does not occur, fine. So, z will be replaced by some function of x, say f of x, y is not important there. So, it gets T y and B x y implies P f of x and R x f of x. Okay, the first one. Then of course, this will be omitted, all this we get, but then we need clausal form, right. This is implication, you have to bring it to C and F. So, this will give not of T y and B x y or P f x and R x f of x. Okay. Now, you have started omitting this. Okay. So, that will give what? Not T y or not B x y or P f of x due to De Morgan and R x f of x. Yes, any problem, right? Next we distribute, because we want C and F. So, this gives not T y or not B x y or P f x and not T y or not B x y or R x f x. Okay. So, now we have the clauses as this is one clause, right, not T y or not B x y. So, let us write the clauses or P f x, one more not T y or not B x y or R x f of x. Next from this not P o, next T b, next B a b. But before applying resolution, we need to see that they do not share a variable, still these two clauses share a variable, right. So, we should rename the variables before applying resolution. So, here we have y repeated, x is also repeated, fine, those two we have to rename. So, let us rename here itself, we get T v, y is v, x is let us say w. So, this is the set of clauses from which we have to get bottom by resolution. We should have a resolution refutation of this set of clauses. So, these are the clauses. Now, how do we go about? We should have a strategy. Say T b and this might resolve quickly. Okay. So, let us start with T b, it is a hypothesis. Second, we introduce not T y or not B x y or P f of x. Now, use the resolution. So, T b, not T b, not T y, they unify with y as b, that is the most general unifier. So, you substitute y with b here, forget those two, take the others, right. So, resolution gives not b x b or p f of x, 1 2 resolution with x as y as b. Okay. Next we have BAB, let us introduce that. So, BAB hypothesis, again we resolve. So, x should be replaced by a, that is the most general unifier of not of BAB, BXB. So, you get P f of a. So, this comes from 3 4 resolution with x substituted by a. Okay. Now, not PU is there, so they will resolve not PO hypothesis, and 7 is bottom not of this unifies with u substituted by f of a. So, 5 6 resolution with u substituted by f of a, that is it. We have never used this. Okay. Fine, that is how resolution will proceed. Let us take one more example. So, like suppose you have some b plus c equal to d plus c, right. How do you proceed? Proving that b equal to d, that is your cancellation law in groups. Okay. So, what you do is take b plus c plus minus c on both the sides. Okay. Minus c is the inverse of c. Then we use associativity. So, it was like this earlier, right. Then we use associativity to get b plus c plus minus c equal to d plus c plus minus c. Okay. Then we use identity element. So, give b plus 0, d plus 0, that is definition of inverse itself, right. Next property of identity element. So, you write b equal to d, that is how you proceed by informal arguments. Okay. So, what have you used? Existence of inverse element, property of the inverse element, that becomes 0, and associativity, and then property of the identity element. These are the things you are using. Okay. So, let us see what are the axioms of the group itself. Fine. So, the group axioms you are using is, okay, what are available? One is your closure rule, right. For every x and y there is z such that x plus y equal to z. Okay. So, for each x, for each y there is z such that x plus y equal to z. That is your closure of the addition. Next we use say associativity. So, it says for every x, for every y, for every z, x plus y plus z equal to, so let us write equal to this way, x plus y plus z. Okay. Next identity element. So, identity element says there exists something which behaves like your identity, right. Is that okay? So, that is for any x. So, you say there is x for every y such that y plus x equal to y, that is what you have used here, right side only, left side I am not taking. Okay. One more bracket should be there, na? Here it ranges over everything in associativity. Fine. Next you have the inverse element which says for each x there is y such that x plus y equal to that 0, 0 element which is the identity. So, here we are telling call this x, there is x for every y, call this as 0. Okay. So, you can include directly as 0, does not matter, a constant, you can use that constant. Let us simplify it, it will be easy for us. So, there exists x, that x is called 0, so we just take it. Now, it is combined, right. So, then we say for every x there is y such that x plus y equal to 0, y is the inverse of that, fine. These are the 4 axioms of the group. Now, when you write in Clausal form, how will they look? First thing is you cannot write this plus symbol, that is a function of, it is a binary function, two-ary function, say f of x y, right. Next equal to is there anyway, 0 will introduce as it is. Then one more is this one, for every x there is y, so when you scolemize it will say x plus some h of x equal to 0, right. When you scolemize this, so this y will depend on x automatically, so that means x plus some h of x equal to 0, right. So, that will be our clause directly. So, let us write the in clause form, it will look like f of, we start from this f of x comma h of x, okay, equal to 0. So, equal to some constant, which constant we will write, we can write 0, but let us write c in our language, just omit it, no? Clausal form. In Clausal form every free variable is universally quantified, right. So, directly writing the clauses. Next for every y, y plus 0 equal to c, so that is f of y comma c equal to y, okay. This one. Next this one, how do you do? For every x, for every y there is z, x plus y equal to z. So, this is really f of x plus y. So, f of x plus y exists for every x y, that is what it will say, right. We assume that implicitly, we do not have to worry, fine. Or you can say this z depends on x and y, so write z equal to some function, this is already f of x y. So, f of x y equal to g of x y, that is what it will say, fine. Let us go to next one, associativity. So, that you can write as f of, let us not use x and y, right, say u, v and z, already two clauses are there. So, let us write u again f of u v comma z, z we can use equal to f of u comma f of v comma z. Okay. Abelian group is not required here, right, we are just taking a group, is that fine. Next we wanted to prove the cancellation law. So, there is a premise given, premise is b plus c equal to d plus c, okay. From there this c is cancelled, you get b and d, that is what, fine. So, now we have already used c, let us change something, so let us write e, let us write as e, fine. So, now something is given f of b comma c equal to f of d comma c. Okay. From which we want to see that this entails b equal to d, fine, that should be our conclusion, this entails b equal to d. So, we also assume not of b equal to d and try a refutation of this. Fine, this is the formulation. Now, I have to go for the resolution proof. B plus c equal to d plus c. Let us start from there. So, that says f of b c equal to f of d c, hypothesis. Okay. Next, what we are doing, b plus c we are adding with minus c. So, that means f of whatever is given comma h of c, right, inverse, that is our h now. So, comma h of c. How do we do that? From this we want to see that f of f b c comma h c equal to f of f d c comma h c. We want this to follow. Which rule will allow it to do? See, it is the closure rule that is allowing us. This rule is allowing us. Whatever x y you take, you can add them to get an element, right. So, that is assumed because f of any term will be another term and terms can always be interpreted. So, it is implicitly there in the semantics, fine. Once it is a function, its semantics allows that there is an element, but then within resolution how to infer it, that is the problem. Say f of, take some p, does not matter, okay, call it a variable. Now, p h of c equal to f of p h of c, equality, that p. If you want, you write s, first time you are using. So, let us write s instead of p, s is there. So, that is your x s. Now, this x of s when we write, it is not necessary that every s will be substituted, it is not a variable to be substituted by a term. Any occurrence you can specify, that occurrence will be substituted, everything need not be substituted, right. So, that is the freedom we have with paramodular. So, here suppose you take this s and unify this t, this is your u, fine. With t and u, you delete that clause t equal to u, you delete x s and introduce x of u, in place of s you are using some u. So, let us write here this s I am replacing by u, it is there, okay. The other s I do not have to replace, it is kept as it is, fine. So, now what happens, if that is my s, this is my x where s is there, x s will give me x of u. So, here it should have been s, right, that is your x of u, is that okay. U is f of d c, t is f of b c. So, t equal to u is deleted, in x of s one s or many s's you can substitute by that u. So, that is what I have done, u, other one is left as it is, fine. So, one step is okay. This is the third one, which is obtained from 1 and 2 by paramodulation. So, in fact, it is the sigma s t, remember, if that is your s and this is your t, then on x u you have to apply sigma, right. So, what is your sigma here? MGU of S and T, two terms S and T, right. S is a variable here, S, T is f of BC. So, their MGU is S by f of BC, right. So, this paramodulant should have sigma as S by f of BC. So, this S will be f of BC. Is that clear now? So, it follows by paramodulation. So, what I do? I take T equal to f of BC, U equal to f of DC, right. So, I have one clause T equal to U, another clause x of S. So, what is my x of S? This S, I forget this. In that formula this S I am concentrating, that is x of S. Okay. Now, I have to delete T equal to U, delete x of S, introduce x of U, right. So, x of U means this S will be replaced by U. So, here it is S, fine, here it is U from this, okay. That is my x of U, where S is here, fine. But then paramodulation says on x of U apply sigma. Sigma is the most general unifier of S and T. So, S is here, T is here, their most general unifier is S by f of BC, that when applied on H of U, x of U, S is replaced by f of BC. So, directly this comes. Yes. Yes.
So, is it allowed to take x of S as part of one?
Yes, that is what paramodulation says. You do not have to replace everything. If you replace everything, then there is no meaning of taking most general unifier, right. So, one or many instances of that S can be seen, you can identify them as x of S. So, there is some non-determinism there, right. Suppose there are many occurrences of S, I can take only one occurrence, I say this is my x of S, everything is in X, that S I will be substituting. I can take identify 3 or 4 even, all of them will be substituted at a time, the other one S will be remaining, right. I can introduce everything also S, suppose everything S, then it becomes f of DC HC, f of DC HC, that is all. Okay. So, this requires some practice of paramodulation.
And some by T at the end of the day.
Yes, that is right, because T equal to U, that is what paramodulation means. Since T equal to U, wherever S occurs, some of the S I can replace by T, some of the S I can replace by U, paramodulation allows it, right. So, that is what we really need in this argument, we are doing like that, no? Some of them I replace by B plus C, some of them I replace by D plus C in my expression, okay, clear. Now, let us go further. So, what is the next step we have done? Associativity, we have used associativity on both the sides. Now, associativity we have one clause for that. So, use that f of, what is our clause in terms of u v z, u v z equal to f of u comma f of v z, right. This is our hypothesis, it is available with us as a clause. Now, what we want here is this z should be HC, this f of BC, u should be B, v should be C, then one side of that will come, right. Is that okay? But what we get here is f of BC HC will be giving f of B comma f of C HC. So, 2 steps will be required, at a time you cannot do here, fine. So, what we want here is that from this and this we should get f of BC comma h of C is equal to f of B comma f of C comma H C, right. This would follow one side of it. Okay. That is again paramodulation. Yes, with what? Paramodulation with what? With what you will be taking that paramodulation? Suppose you take t equal to u here, this is my t, this is my u, right. Then this is my x of s, s is say z or something. Okay. Now what you do? Z should be replaced by something. Which thing you will replace? Z will be replaced by HC. Then, but you will introduce d again. If you take t equal to u, then when you take x of t, it will introduce the whole thing here. Do you see? See the problem or not? First you have to realize the problem. See, from these two you want to infer this. How do you infer? With associativity. What do you say? U should be substituted by B, V by C, Z by HC. But that is, which rule allows that? Which rule will allow that from this it will follow? Yes. Okay, let us see temporarily. You have Px, you want to infer Pc from it. How do you do it? You cannot do it here in resolution. There is no rule to do it, right. So, how to get this in resolution? You can write it as a derived rule once you do it. Before it you cannot do, right. You have to do through resolution only. Now, how to do it by resolution? From Px, how do you infer Pc? Well, this inference we can do twice, say Px and not Pc, and that entails bottom by resolution. Therefore, Px entails Pc, right. But this becomes a derived rule now. If you have x of x1 to xn, and then you can infer x of t1 to tn, that becomes a derived rule. Directly by resolution it does not come, it comes as a meta theorem now. You can use that meta theorem and get it done, right, just by resolution. But paramodulation also can do it. For example, with Px I introduce C equal to C, equality, fine. Now, this is my t, this is my u, this is s. So, t equal to u gone, x s gone, x of u, I get Pc. S is x, that is replaced by u, u is C, and t equal to u. So, most general unifier is empty substitution, right. Sigma is equal to empty substitution itself, because t equal to u. Now, t equal to s, when you take, x will be substituted by C. From t and s you want most general unifier, not t u. So, that is x by C, right. But once you replace this, this becomes Pc, there is no x. So, even if you apply, it does not matter, same Pc remains. So, by paramodulation this follows, right. You do not have to go to resolution again, by paramodulation inside the proof you can do. Then here similarly, if you do, you have to do really 3 steps: B equal to B, then get B, V, Z as it is, then C equal to C, get V by C as it is, then Z equal to HC equal to HC, then Z HC will unify, you will get this. So, 3 steps it will take, right. So, what we do, we will make a shortcut here, we will write phi as B equal to B, C equal to C, H of C equal to H of C, right. We will write equality. then 3 times using paramodulation you get this, right. So, by paramodulation for 5 paramodulation. Okay. Clear how this step is going. Next, similarly this is 6th step. Then 7th, what do we do? From this side we have to do something from the other FDC HC. So, we will again take D equal to D, C equal to C, H of C equal to H of C. Really this, if you do step by step, these two will not be necessary because they are already introduced somewhere, right. C equal to C will be another line, HC equal to HC will be another line. So, you can again use those two, you do not have to write, but this is a better mnemonic for us that we are using these things. Then 8 will be f of DC HC equal to f of D f of C HC. This is 6, not 6, 7 and 4 again, right, 4, 7 paramodulation. What we have got? F of FBCHC equal to B FCHC, f of FDCHC equal to FD FCHC. From these two you wanted to conclude these two are equal, right. It is like x equal to y, and then what else? We have x equal to y, then y equal to z, then x equal to w, therefore z equal to w. 3 things will be used. This one 6th, 8, 3, 6 and 8, right. See, f of BCHC equal to f of DCHC. Now, f of BCHC equal to f of BFCHC, therefore, these two will be equal. Again the other one will be used and to conclude that step, right. Now, from 3 and 6, let us see this one 3 and 6. From these two we wanted to conclude f of BC B C H C is on the left side. So, this one, these two will be coming f of B comma f of C H C equal to f of D C H C. Look at 3 and 6. This is one, say alpha, first one is also alpha, right, alpha equal to beta, alpha equal to gamma. So, you want beta equal to gamma, we wrote as gamma equal to beta. Okay. Now, how do we get it? Okay, let us take it in that form, alpha equal to beta, then we have alpha equal to gamma, we want gamma equal to beta. This is how it should come, right. Does it follow by paramodulation? So, let us take alpha equal to beta as t equal to u. Finally, you have something, beta is there. So, this is t, this is u. Now, S is what? Alpha. Let me identify this as alpha, okay, or this as alpha, something, one of them I have to take as a S. Then what happens? S will be replaced, this will be going, this will also be going, I have to take x of u. So, suppose I take alpha as S, then this will become beta, beta equal to gamma will follow. Is that right? So, let us write that way, say beta equal to gamma, that will follow. If I take this as t, this as u, this is my t, this is u, this is s. So, this is my xs. So, finally, x of u equal to whatever it is, x of u is beta equal to gamma, and s t their most generally unifier is empty because they are same here. right. So, it will follow beta equal to gamma, fine. So, let us write then in that form instead of this form. So, we get f of dc comma hc equal to the other one f of b f of c hc. Okay. This follows by 3 6 paramodulation. You have empty substitution as the most general unifier. Clear? Next you want to use what? 3 and 8 similarly. Okay. If you use 3 and 8 f dc that will be your alpha now, right. That common thing is your alpha, and one of them is beta, the other one is gamma, right. So, which side you take, it does not matter, this will be equal to this, right. We have already f of bc hc, so we can write that. So, we can write 10 is f of b f of c hc equal to f of d c hc. This is again 3 8 paramodulation. We want really one of these, we do not need both of them, any one of them should have done, right, is it not? See dc and hc we want to combine, so they are combined here, bc fc we wanted to combine, they are combined here. Okay. So, what we want is we should have b fc hc and d fc hc, that is what we have got. Okay. So, then to get it you have to use what? 3 and 8, does 8 give? F dc is f d of fc. So, these two are combined, these two will be same, then you get bc, not this. If you use that 3 8 you would get in this form f bc hc, in this form you will get, that is what, that is what we wanted in this form, right, right, we want the other format, not if you use 3 you will be getting this form only.
Use 8 and 9 directly.
Yes, 8 and 9 if you use we will get the required one. Clear? So, we really wanted this form f of b f of c h c. So, you have to use 8 9 parameters. So, this is only the trickiest part in the resolution method, because it depends on which one you want, that is how you will be choosing the premises and getting the conclusion. Now, once this is done we have come up to this stage of our argument, fine, this stage really. Now, you have to go for c plus minus c equal to 0, that is to be done. So, that means c h c should be replaced by 0 now, which premise gives that x equal to e, f of x h x equal to e, that is a hypothesis. Now, with this we want to substitute, get c and x equal to b you want, no, f of c h c only you want, right. So, c equal to c is required, it is already introduced somewhere, 5 there, okay, 5 there, let us forget this, this is only for our reference, it is already there. In fact, this 5 will be 5 prime 5 double prime, 2 stages are there, okay, that is already there. So, then we say 12th, that gives f of c h c equal to e. So, that is from 5 11 paramodular. So, these heuristic rules really help Once we know one equality is there, it will follow like that, Px then Pc will follow. How? By introducing C equal to C. Okay. Then similarly 13 we want D equal to D, that is in 7. So we get f of D. No, that is not required, we do not require this, right. From this we can go. Now 13, what we will get here? This is your T, this is your U, right. This is your S completely. Okay. So replace them, you get f of B comma U, which is E, right. So it will come in f of B E equal to f of D. You can take this S also simultaneously, many S's you can take at the same time. So this will erase the E. So this gives 10, 12 paramodular x of U. So you can identify both the S and then replace. So we are at this stage now, B plus 0 equal to D plus 0. Next we need a premise. Which one? F of y equal to y. So 14th, f of y e equal to y, that is the hypothesis. Okay. So again we need here is what? 5 is B equal to B. So take here. So 5, 14 would give f of B E equal to B, right. You need B equal to B there. So that is your 5, 14 paramodulation. 16 will be f of D E equal to D. Similarly, but that is in 7 now. 7, 14 paramodulation. Okay. Then from this 13, 17 is 13 and 15, 15, 16. Then you need 13. So let us say 13 and 15. 13 and 15 would give B equal to F D. Okay. So 13, 15 paramodulation. Next you need one more, 18, that gives 16, 17, B equal to D. Next, it is not over, hypothesis. '18, 19 resolution. Okay. So that is how we have to proceed using paramodulation. But recall the heuristics we have used, those things will be really helpful.